All right, let's dive right in. If you work with next-generation sequencing, you know exactly what I'm talking about. The data is just massive. So the real trick is, how do you take that absolute mountain of information and turn it into an evolutionary tree you can actually stand behind? When you can publish with confidence. Well, that's exactly what we're going to map out today. This is your guide to building a truly defensible tree. And yeah, this really is the heart of the matter. NGS has given us this ocean of data. We're talking billions of tiny DNA reads. It's kind of chaotic, right? So the big question, the one we're all trying to answer, is how do we possibly wrangle all of that into a single, reliable tree of life? That's the puzzle we're going to solve. And we need to be super clear about why this is so critical. Because, look, every single phylogenetic tree you build, that's a scientific claim. And its entire validity, its truthfulness, it all comes down to the methods you pick to build it. Make one wrong turn, choose one tool that's not quite right for your data, and you could end up with a result that is just, well, flat out wrong. Seriously, the stakes are that high. Okay, so here's our game plan. We're going to start by laying out the tree building challenge itself. Then we'll walk through the essential steps. First, getting to know your data. Next step, the alignment. Then we'll talk about the inference frameworks, the engines that do the work. And finally, we'll cover how to validate and report your findings. All right, section 1, the tree building challenge. And honestly, it boils down to this paradox of choice. The amazing thing about NGS is also what makes it so hard. There are just so many tools and methods out there. It can be overwhelming just trying to figure out where to begin. So the solution isn't some single magic piece of software. It's not that simple. The answer is having a structured process. It's all about making a series of smart, deliberate choices. You follow these 4 steps, and what you get is a workflow that's not just logical, but actually defensible and perfectly suited to your data and your research question. Okay, that brings us to step 2, which is really our first major move, getting to know your data. This is the absolute foundation of your phylogeny, and I'm not kidding. Everything else we're about to discuss completely depends on this. You've got to understand its quality, its completeness, and of course, the sheer scale of it all. And this is where we hit our first major fork in the road. And it all boils down to the quality of your data. So on one side, if your data is, let's say, a bit messy, maybe it's fragmented or you have low coverage, you're probably going to lean towards alignment-free methods. These use some clever statistical shortcuts, like counting little DNA words called K-mers, to get a fast, rough idea of how things are related. But if you've got that beautiful, high-quality data from some nice conserved genes, then you can use the gold standard, alignment-based methods that let you model evolution at every single site. The other huge factor here is just pure scale. Once that number of sequences you're working with, what we call N, starts to climb past, say, 10,000, well, a lot of standard tools just can't handle it. They just break down. They get so incredibly slow that your analysis could literally be running for weeks, maybe even months. That number, 10,000, it's a real line in the sand where you have to completely rethink your strategy. So how on earth do you deal with those massive, ultra-large data sets? Well, the smart play is to use a 2-step approach. First, you grab a really, really fast tool, something like FastTree, to build a quick and dirty backbone topology of the whole thing. Then, once you've got that general shape, you can zero in on the specific branches you're really interested in and reanalyze just those smaller sections with your more precise but slower methods. All right, so let's say our data is good enough and we're going with an alignment-based approach. That brings us to our second big step, the alignment. The multiple sequence alignment, or MSA. The entire goal here is to carefully line up all of our sequences so that we're comparing apples to apples, right? We're trying to figure out which specific positions or residues in each sequence actually share a common evolutionary origin. And not all alignment tools are created equal. The best one for you totally depends on your specific question. For example, if you need to factor in protein structure, a tool like MAFFT-DASH is fantastic because it integrates that data. Are you trying to compare really distant relatives? Then you might look at tea coffee, which is great at stabilizing those tricky alignments. Or maybe you just need a great balance of speed and iterative refinement. For that, muscle is a classic go-to for a reason. All right, we've come a long way. Our data is prepped, it's all aligned. Now it's time for the main event, choosing the inference framework. This is the engine that's actually going to build our tree. This is the step where we feed our alignment into a complex statistical model and ask it to figure out the most likely evolutionary story. Now, in this world, there are really two main philosophies. First, you've got maximum likelihood, or ML. This is the absolute workhorse of the field. It's laser-focused on finding the single best tree topology and branch lengths, and a tool like IQTree2 is an absolute powerhouse here, especially with its automated model selection. Then, you've got the Bayesian framework. This is what you reach for when you want to do more, like jointly infer the topology and estimate divergence times using molecular clock models. That's where tools like Mr. Bayes or BEAST really shine. But what if you're facing some serious resource constraints? I mean, these complex models can take forever to run on huge datasets. It's a really common problem. Well, the modern solution is to leverage GPU acceleration. Tools like RAxML-NG or BeastX are designed to use the power of graphics cards, yep, the same kind of chips in gaming computers, to dramatically speed things up. You can maintain that model complexity but seriously cut down on your runtime. Okay, so you've run your analysis, you have a tree. Awesome. But, and this is a big but, we are not done. This final step, validation and reporting, is arguably the most critical one for ensuring your research can actually stand up to scientific scrutiny. You have to check your work and be totally transparent about how you got there. I like to think of this as the 3 pillars of a defensible phylogeny. First up, model selection. Do not, I repeat, do not just use the default settings. You need to compare different models and justify your choice. Second, robustness checks. You've got to test how stable your tree is. This is where things like bootstrapping come in to see how much support each branch really has. And third, and this is non-negotiable, reproducibility. You have to document everything, software versions, all the parameters, the exact command line flags. Someone else should be able to take your data and your notes and get the exact same result. And when you put it all together, this is the goal. You want to construct NGS-based phylogenies that are both computationally efficient and scientifically defensible. It's about finding that perfect balance between getting the job done with these massive datasets and making sure the science behind it is absolutely solid. So I leave you with this question to think about. Your phylogeny isn't just a diagram. It's a scientific claim, a strong one. So the real question you need to ask yourself isn't just how do I build it, but how will I defend it?